This video is a breakdown of the plant wire SimPrep node for my Procedural Plant Toolkit. This node will take the wires used to construct the plant mesh and prepare them for simulation, with the intention to use the animation from the simulated wires to drive the deformation of the plant mesh down the line with other nodes in the toolkit. This node takes in the plant wires and plant mesh and spits out the processed plant wires through the second output and any created constraint geometry through the third output. The first output, however, is reserved as a utility used to visualize various functions within the node. This node has a few setup parameters, the first being to fuse each wire to its parent to connect the branches inside of the simulation. It can also clean the attributes used to construct the plant mesh that are no longer necessary, and create a group of the first point of each trunk wire for an easy pin group. It can also group all the points fused together to connect the wires. The final setup parameter specifies which solver to set up the geometry for, either the vellum solver or the wire solver. This adjusts the behavior of the tool, modifying or bypassing functions to better prepare the geometry for the stipulated solver. For example, the function to ignore problematic collisions is vellum specific. When the solver is set to the wire solver, this function is bypassed and the parameters are hidden. But for the vellum solver, this function will find every initial collision. It'll filter for which collisions are problematic. Then it'll create the attributes to ignore these collisions. This is done because vellum will shrink collision radii to avoid intersections on the first frame, and this can cause some pretty bad clipping issues whenever this animation is transferred back over to the plant mesh. However, we want to make sure not to ignore valid collisions that could create more clipping by allowing branches to swing through each other. That is to say, we want to ignore unrealistic collisions like a branch trying to collide inside of itself, but we want to respect the valid collisions between two branches that might be touching on the first frame. Now this function can be modified, so to see what we're doing, we can set the visualize parameter at the top of the node to the collision ignore function. Here we can see the collision radii of each point represented as a sphere, with the blue spheres representing a populated collision ignore tab. The ignore collision menu sets the basic behavior of this function. By default, it is set to ignore collision conditionally. That is, to detect all the initial collisions and then to filter for which collisions to ignore. However, we can choose to completely bypass these filters and to ignore every found collision, or we can choose to disable this function entirely. If we do choose to ignore collisions conditionally, we can set which conditions to filter for, as well as the tolerances for each. For example, we can choose to only ignore collisions between sibling branches at the base. We can choose to add a little bit of tolerance so small overlaps are not ignored. To see the collision ignore in action, we just need to pipe these wires into a vellum solver, and we can see that the collision radii which intersect on the first frame do not shrink in the subsequent frames. This node can also create attributes to describe how the plant should behave inside the simulation, slight variations depending on which solver is specified. For example, in the More Attributes folder, both rest and friction can be set for both solvers, but when the wire solver is specified, a anchor point ID and width attribute become available, with the width being created by default since it's used as the collision radius for the wire solver. However, the mass toggle disappears for the wire solver since mass is set on wire objects inside the .NET. Whereas for vellum, we can toggle on the mass and create mass from a density input, though we can also choose to read the density attribute or to scale the density attribute by a constant. Attributes to describe the stretch stiffness and bend stiffness of the plant wires can be created for both solvers. However, the attributes' names will conform to the naming convention of whatever solver is specified. So for the vellum solver, the output attributes will be stretch stiffness and bend stiffness, whereas for the wire solver, the output attributes will be k-linear and k-angular. However, we can override these attributes' names with a custom name. For example, we can specify that this is the stretch stiffness of the tree. Both stiffnesses are mapped using an identical set of parameters, and both can be visualized as a color gradient using a linear or logarithmic scale. The domain is set to radius by default, but it can be changed to distance or to a custom attribute if desired. The domain can also be flipped and clamped as needed. The stiffness range can be modified from 0 to 1, although the coloration will not change since the color gradient is normalized. The ramp used to map stiffness by the domain is accessible to the user, so you can create stylized effects if desired, like this. We can also sharpen or round the distribution of the stiffness, and the stiffness can also be decayed proportional to its relative position in the hierarchy as seen here. This node can also help to constrain movement inside joints where branches are connected with their siblings. That is to say, this node has a function to detect joints such as the whorl on top of this trunk or this fork where the branches are connected at the base inside the joint. Then the function will create the proper data to constrain the plant wires so they stay connected inside the simulation. This function can be visualized to see which joints are being found. At each cluster of spheres is where an interlocked joint was found, with each of the spheres indicating the collision radius of an interlocked point. This search can be modified if necessary. So if the search was overzealous and too many joints were found, the search radius can be scaled down. And if some joints are missing, then the search radius can be scaled up. This search can be limited to the inside of joints of a Boolean mesh. Now for these joints here, there will be no effect since all of these branches are connected here inside the joint. However, if we swap this plant mesh out for a variant where only the trunk joint is Boolean together, then whenever we activate this function, all these joints are no longer detected and only these points will be found. This search can also be restricted to a branch level range, that is, a branch's relative position in the tree's hierarchy. So if we toggle on this behavior and set the branch level range from 0 to 1, only the trunk and the trunk's child branches will be constrained. So how these constraints are created will depend on which solver is specified. For the vellum solver, no constraint geometry is output. Instead, a point group and cluster attribute are created for a vellum constraint node to use to create glue constraints. So we can see here, just specifying the point group, the cluster attribute, and modifying the search parameters a little bit is enough to create these glue constraints. We can also create a stretch stiffness attribute using the overlap of each branch. This will allow us to vary the strength of the glue by how interconnected each branch is. This stretch stiffness can be visualized as a color gradient, and we can choose how to process all the overlap data by using the max, minimum, average, or medium relative overlap amount. We can also set the output stiffness range, and we can modify the ramp we map stretch stiffness by. To increase rigidity, the max stretch stiffness can be used for points buried deep inside the joint. So if we increase the joint size and hit this toggle, you see all the points that are not on the edge of the joint now have the max stretch stiffness. Now for the wire solver, constraint geometry is created for a spring network. We also configure the constraints data, using these naming parameters. First, we need to specify the name of the wire object being constrained, as well as set the name of the constraint itself. We can also specify the constraint type, although this attribute is not created by default. If these naming parameters are properly set, the constraint geometry is ready to be used inside of a constraint network. Similar to vellum, we can map the strength of the constraints using the overlap data. We can visualize the strength and we can hide the spheres since we're mapping directly onto the constraints. And we can set the range of the output strength values as well as modify the ramp that we map strength from overlap with. And the strength of a constraint between 2 points buried deep inside a joint can be set to the max, as seen by this. This node can create a second set of constraints for inosculation, which is when 2 branches are connected outside of a joint. This often occurs in nature when 2 branches grow into one another, and the resulting pressure and friction fuses the branches together. We can visualize this function to see which sites of inosculation were found. And here we'll see the collision radii of all the inosculated points, as well as the constraints between these points. This inosculation was found, even though no points are colliding. This is because capsoid collision is used to detect the inosculation, which allows the inosculations to be found on low-resolution wires. This search can be modified by a few parameters, first being a toggle to ignore collisions already processed by the joint constraints, as seen here. We can also choose to limit an oscillation to only the Boolean branches, which is enabled by default. When we disable this function, we will see that a second site of an oscillation was found, where two branches are simply clipping. Small sites of an oscillation can have their constraints spread to increase rigidity, which is very useful when constraining low-resolution wires. The search radius can be scaled down, and the constraints can be limited to a branch-level range. These oscillation constraints are created same as the joint constraints. For the vellum solver, a point group and cluster attribute are created for a vellum constraint node to use, whereas for the wire solver, the constraint geometry is created and output along with the joint constraint geometry, and its data can be configured with these parameters. Now that this tool has been fully broken down, I want to cap things off with how this tool was designed to be very convenient. It's supposed to be fast and easy to set up. It's supposed to be easy to understand. It can prepare the geometry for both the vellum and wire solver. It can create map useful attributes. It can even deal with the complex issues related to problematic collisions and constraints. This is all to the end that once the user has finally made their plant, they can just throw this tool down. Within a minute, they can already have simulation-ready wires, and they can move on from the technical issues of simulation onto the artistic side. Going forward, I want to generalize this node as well as all the other animation tools of the Procedural Plant Toolkit. I want the nodes to be able to configure the input wires and mesh so that it can work with geometry from different sources, such as the lab's tree nodes native to Houdini or from a different program entirely like SpeedTree.